Okay, here's our next gas law, right? Notice temperature is now going to be constant. And we're going to change volume. Okay. Let's draw our containers. Again, try and make them relatively the same size so we can compare them. Here's my little gauge. Okay. And the second one. Now, because volume is changing, this lid that we have that's right in the middle, it needs to move up and down, right? Because volume is the amount of space. So I'm going to put my lid way down here for this one, because this side is going to be a smaller space. And this here is going to be a bigger space. Okay. For the bigger space one then, right, I'm going to put it way up at the top. You see it? So, let's talk about the space. This space is smaller. We can say it decreases. This space has gotten bigger, so this increases. What has happened to the number of particles? Has it changed or is it the same? The number of particles in my container. Have I put more in or taken them out, or is it still the same?
Still the same.
It should still be the same, so let's just make that down here, right? Number of particles. Remember, that's the variable n down here is constant. So how many particles am I going to draw in my models? Sorry, right? Number of particles is constant. So how many? Oh, okay. How many particles do I draw in? We draw 9, right? So I'm going to draw 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? This one too. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, number of particles stays the same. I should have the same number. What has happened? Oh, when we talk about motion, what measures motion? The temperature, right? What do we know about the temperature? It's constant. So my motion is going to stay the same. how long do I draw my arrows? Are they going to be different or the same? Same arrows. Now notice this has little space, right? So I'm going to start, I got to bounce a lot of these guys, don't I? Because there's not a whole lot of room to draw, right? These guys actually moving in a straight line. These guys are like bouncing off like popcorn. Hold on. Okay, we'll finish. Okay, so remember over here, right, we had arrows drawn in and we had collisions drawn in, right, for our smaller volume, right? If temperature is constant then, what are the arrows going to look like in our bigger volume? Are they going to be smaller, the same, or longer? If it is the same temperature. It should be the same, right? Remember, the length of our arrow tells us the temperature or how fast it is moving. So I'm going to go ahead and I'm going to draw the same, right, length of arrow for these guys here. Maybe some of them bounce off. But you can just draw them, right, whatever direction you want. What do you notice, right, about the number of collisions? Remember I said we're going to model collisions with x's, right? So here's an x, right? Here's an x, there's an x. What do you notice about the number of collisions for this one versus this one? Good. Right, so we should write that. Collisions, there are more, or that it increases. Right, for here, there are less, and so we would say that it decreases. Okay. When you're explaining, when you're talking through and modeling, you really have to show these three things. What's happening to the space? What's happening to the motion of the particles, right? That's our length of arrow. And what's happening to collisions, the x's, the bouncing off. You do also have to model the number of particles, right? But those should always stay the same when we're talking about these particular gas laws, okay? Oh, we should then make our gauge here, right? More collisions means what about pressure? More pressure or increased pressure, right? So I'm going to go ahead and draw that maybe pointing between 3 and 4. And then if there's less collisions, that means I'll point this, right, maybe between the 1 and the 0. Okay. So as volume increases, what happens to pressure? Look at what happened. Yes, it decreases. Right? If one goes up and the other goes down, they are inversely related. Okay? Inversely related. This particular gas law that relates volume and pressure is called Boyle's law. the graph of an inverse relationship, right? If we would label this volume and this pressure, it looks like this. It is actually a curve. I am not drawing it incorrectly, okay? Inverse relationships are curves. They're kind of like a half of a not a parabola. Have you guys heard of hyperbolas? Right? This is like half of a hyperbola. Okay? And the equation is follows. P1 times V1, okay, is equal to P2 times V2. These are variables, right? So when you multiply the initial pressure and the initial volume, it should equal, right, the final pressure and the final volume multiplied by each other. Okay?